So, few additional remarks on simple harmonic motion. In my previous sessions, some basic ideas were communicated to you. The basic algebra and physicality of simple harmonic motion very briefly was spelt out. And essentially what I told you was that if the acceleration, which is like d2x dt2, is some minus omega squared x, where omega square was k by m. K is the force constant for the oscillation, m was the mass of the oscillator. Then the motion executed by a particle that subscribed to this differential equation was deemed simple harmonic, right? Omega was the angular frequency, time period was 2 pi by omega, and so on and so forth, right? The amplitude was independent of that. It depended on how much energy the total particle had, how much total energy the particle had. Now, the solution to this equation turned out to be x equal to some a sine omega t plus phi. That was the solution to this differential equation. Phi was a phase constant which determined at time t equal to 0 the kinematic status of the particle, the position and velocity at time t equal to 0. So phi was like a phase constant. We also looked at the analogy of this motion to the corresponding motion of the auxiliary particle on an auxiliary circle centered at the mean position of this oscillator, having radius equal to the amplitude, and the auxiliary particle having angular velocity synonymous with angular frequency of the oscillator, right? Now, the solution to this differential equation was this. Now, the differential equation, realize, does not understand what x is. And the physicality of x is not understood by the differential equation in arriving at this solution, right? It doesn't understand whatever x means. Now, if there was a differential equation of this kind, d2f dt2, t is any other variable, equals minus omega squared f, the differential equation would be indiscriminate in terms of providing a solution to this equation, because the way it treated x, it will treat x, f. The way it treated x, it is going to treat f, right? So it will throw up a solution of 2f as f equal to, let's say, some f naught sine omega t plus phi, right? F could be any variable, f could be any variable. But if a variable subscribes to this differential equation, then it's called a simple harmonic variable. It's called a simple harmonic variable. Then no matter what it means physically, the mathematical solution that emerges out of this differential equation would be f equal to f naught sine omega t plus phi. Yes or no, right? Now, suppose there was a string which is fixed at the end A. The end A of the string is fixed, okay? And there is a light massless ideal string that connects A to a mass m. That connects A to a mass m. Initially, let's say it's in a vertical state. Initially, it's in a vertical state, and the length of the string is, say, L. Very slowly, I displace the string from its vertical position. I displace it by an amount, say theta. This string of length L, right? Now, at this juncture, there is mg acting like this. There is tension in the string T like this. This angle is theta. This is mg resolved as mg cos theta this way and mg sin theta along the tangent. Right? No, T is not mg cos theta. Now, at this juncture, let me look at the torque acting on M about A. Net torque acting about the point A. What are the forces acting? Mg and T. What's the torque of T about A? 0. Why? Because its line of action passes through A. So moment arm is 0. Right? What's the torque of mg cos theta about A? 0. Because the line of mg cos theta passes through A. Realize that mg sin theta is along the tangent and therefore perpendicular to L, right? Mg sin theta produces a non-zero torque about A. Mg sin theta produces a non-zero torque about A. Mg sin theta into L, perpendicular distance of A from the line of action of mg sin theta, right? So it's mg sin theta into L is the magnitude of the torque, net torque acting on M about A. Yes or no? Right? And in this case, if I have displaced it anti-clockwise, realize that I have displaced it anti-clockwise from the vertical position by an angle theta. This is anti-clockwise displacement. The torque is clockwise, right? The torque of mg sin theta about A is clockwise. Do you see that? It's a clockwise torque. Which is opposite to the anti-clockwise displacement. Opposing the anti-clockwise, ACW is anti-clockwise angular displacement. Opposing the anti-clockwise angular displacement theta. Yes or no? That means if I try to displace it in the anti-clockwise sense, then the torque would be in the clockwise sense. That means the torque is opposing the angular displacement, right? The torque therefore should be looked upon as a restoring torque. The torque therefore should be looked upon as a restoring torque. It tries to bring back the bob in the vertical position. Now, let me call clockwise, anti-clockwise torque positive, clockwise torque negative, right? The net torque about A, see, torque about any point is going to be what? Moment of inertia about that point into angular acceleration alpha into angular acceleration alpha, yes or no? But angular acceleration alpha is rate of change of angular velocity, but omega itself is d theta dt. D theta dt will give me omega, yes or no? So if I write omega as d theta dt, this is going to be I about a into d dt of d theta dt, right? So the torque about A is written as I about A into d2 theta dt2 this is IA is moment of inertia of the bob about A, the particle M about A, right? Now this is the torque in at all times, and in this case the magnitude of this torque is mg sine theta into L. But since it's clockwise, I would write this as minus mg sine theta, because I've chosen anti-clockwise positive, clockwise negative, say. So then this torque should be written up as minus mg sine theta into L, right? That's the magnitude of the torque, but written negative because it's clockwise. I'll choose anti-clockwise torques positive, clockwise torques negative, and therefore this equation, yes or no? The minus sign physically also means that it's a restoring torque. Like we had in F equal to minus kx, the minus actually also symbolized that it's a restoring force. In this case, the minus in that context symbolizes that it's a restoring torque. It's a restoring torque. Now, what is the moment of inertia of this mass m about A? ml squared, right? Summation mi squared. So m into square of the distance from A, ml squared, right? So this IA can be written as ml squared. So ml squared d2 theta dt2 is minus mgl into sine theta. Yes or no? Now, if theta is very small, a good approx and in radians, very small in radians, yes, then a good approximation is sine theta equal to theta is a good approximation in radians if theta is very small. Then this sine theta I can write as theta. So this is minus mgl into theta. Or this gives me d2 theta dt2 equal to minus g by L into theta. See, can I remove this? d2x dt2 is minus omega squared x. X was the harmonic variable. This was linear simple harmonic motion. This was linear simple harmonic motion. Simple harmonic motion in x. X was the harmonic variable. In this case, theta is the harmonic variable. It's simple harmonic motion in theta. It is simple harmonic motion in theta. which means now the manner in which theta varies with time should be, the solution to this equation must be theta equal to theta naught sine omega t plus phi, where omega squared now must be equal to g by L. This must be the solution to this equation, where theta naught is the maximum theta possible for this motion. And this is called the angular amplitude. Theta naught is called the angular amplitude. Which we have assumed for all practical purposes to be very small. Maximum possible value of theta is theta naught. Maximum angular displacement from the vertical position is theta naught. You know what I'm saying? Now, in the vertical position, what are the forces? mg and t. What's the net torque about A now? 0. Because both T and mg have their lines of action passing through A. So in that sense, in the vertical position, there is rotational equilibrium. Net torque about A is 0 means rotational equilibrium, right? In F equal to minus kx, at x equal to 0, there was translational equilibrium. Net of all forces being 0. In this case, in the vertical position, net of all torques about A is 0. So this, in that context, is a position of rotational equilibrium, right? And this then is called the mean position of the oscillator. Theta varies harmonically now. Instead of x varying harmonically, theta varies harmonically as per this, right? In this case, omega is the angular frequency of the oscillator, and this kind of an oscillation is called angular SHM. This is angular SHM. F equal to minus kx gave me linear SHM. This will give me what is referred to as angular SHM. This is angular SHM, angular simple harmonic motion. The minimum time. So the kinematic status would be governed by two things for the particle. Theta will give me the position, and theta dot, that means d theta dt, would give me omega, the angular velocity. So theta and theta dot together constitute the kinematic status for this oscillator. And theta dot replicate themselves completely in a time equal to 2 pi by omega. Complete replication of theta and theta dot, like in x equal to a sine omega t plus phi, x and x dot got completely replicated in a time equal to 2 pi by omega. In this, the particle was brought back to the same theta in the same direction of motion in a minimum time equal to 2 pi by omega. So this was the smallest time in which the particle not only came back to its original state, but also with the same direction of motion. Both theta and theta dot is angular velocity, got completely replicated in this time. This then is the time period of motion. This then is the time period of motion for this particle, which is 2 pi root L by G. And this arrangement essentially is called a simple pendulum. This arrangement is referred to as a simple pendulum. Right? And the vertical position is the mean position, where the net torque about the point of suspension A is 0. Otherwise, how could you have said sine theta equal to theta? If the maximum itself is very small, then every other theta which is less than theta naught would be small, and the approximation sine theta equal to theta would hold legal for all thetas. If theta naught, which is the maximum theta itself, is very small, then all other thetas would be very small, right? In fact, just a little beyond, but not required, if theta naught, which is the amplitude, is not very small, then a superior approximation to the time period, if it is not very small, is given by 2 pi root L by G into 1 plus theta naught squared by 16. It's not required really, but just a passing reference. If theta is not very small, if theta naught, the amplitude of motion, is not very small, then the time period of a simple pendulum is going to be 2 pi root L by G into 1 plus theta naught squared by 16. Yes, that's the first level of approximation that we could arrive at. Right, right, right. Never told you the limitations, etc. of this formula. Right, right, right. It was difficult to suggest to you how and why it happened at that time. Right. I mean, all of us went through that phase. Right. Now, let me look at variants around the simple pendulum. This was a situation in which the point of suspension A was fixed, right? We will examine what happens in the event the point of suspension is accelerated, right? So this time, we'll look at the point A, the point of suspension, having an acceleration, say, A. Let's say this angle is beta. This is the bob of mass m, and there is mg acting downwards. A having an acceleration a naught. The acceleration of the point of suspension is a naught. Now, in a frame of reference attached to A, if I have to look at the free body diagram of this, then in addition to mg, there is going to be a pseudo force. Remember that? Ma like this. There is going to be a pseudo force Ma like this. Now, the effective G was G earlier, right? Now the effective G for this situation would be the resultant of this G and this A would be the effective G. G would get revised. G would get revised. Now the effective G for the situation. See, time period 2 pi root L by G. This time the G gets revised. The effective G would be the resultant of this G and this A. A because of this. The resultant of these two will give me the effective G for this situation. And this would be G in a frame of reference attached to A, the point of suspension. This would be G effective. This would be G effective. And from parallelogram law of vectors, angle between A and G being beta, the G effective square is going to be a square plus g squared plus 2ag cos beta, right? That's effective G, right? So time period is going to, the effective time period in a frame of reference attached to A is going to be given by 2 pi root L by G effective, where G effective is the vector sum of this G and this A, making an angle beta with each other, right? Now, if A was to be, if the point of suspension A were to be moving upwards with an acceleration A, then what would happen to beta? Beta would become 0. If the point of suspension, see, this could have been attached to an elevator which is moving up with an acceleration A, then beta would be 0. Now if beta is 0, this will become A plus G whole square. Cos beta is 1. This will become A plus G whole square. Then the G effective in this case is going to be G effective squared is G plus A whole squared. So G effective is going to be G plus A, right? As you expected. G effective is going to be G plus A, right? The time period then for such a situation is going to be, time period is going to be 2 pi root L by G effective, which is G plus A. Clear? Suppose it was the point of suspension were to be moving down with an acceleration A. Then, do you realize beta would become pi? This would be a situation where beta is pi. And this would become minus cos beta, minus 1. This would become minus 1. So this would become G minus A whole square. G effective then would be G minus A, as you expected. The time period then, if it were to be moving downwards with an acceleration A, the time period would be 2 pi root L by G minus A if it was to be moving down with an acceleration A. Right? Suppose now suppose now I have a trolley in which there is a bob of mass m suspended from the point A of the ceiling of this trolley. This is a string, light string, and this moving to the right with an acceleration A. So this is a time period in an accelerating carriage, accelerating horizontally. Clear? Now very clearly, in a frame of reference attached to the trolley, there is mg acting downwards, right? And pseudo force ma acting leftwards, right? So the effective G would be the resultant of this G and this A. This will give me G effective. This will give me G effective. G effective then in this case is going to be root G square plus A squared would be G effective for this time period, for this pendulum. And the time period therefore is going to be 2 pi root L by G effective. G effective is root G square plus A squared. That's G effective. Right? Fairly simple. Got me? Suppose this trolley was placed on an inclined plane. Suppose this trolley was placed on an inclined plane. Clear? So this was the trolley. I'm not drawing the wheels because it adds to the clutter, right? And it was freely moving down. It was freely moving down. If it freely moves down, then it will have an acceleration. The trolley will have an acceleration. Suppose this angle is theta. Then what would be the acceleration of the trolley? G sine theta. G sine theta would be the acceleration of the trolley. Right? That's going to be the acceleration of the trolley if it were to be freely moving down. And now you have a pendulum attached to the point A. This is mg. Right? What then would be the time period of this pendulum? So what you do is, so there is G like this. Think of the point A and just bring it here for convenience, for representation. Then in a frame of reference attached to the trolley, there is going to be a pseudo force MA like this, right? So there is going to be an acceleration A, which is G sine theta like this. Yes or no? If this angle is theta, this will be theta. The angle between G and A is 90 plus theta. Is 90 plus theta. In this case, that beta that we were talking of is 90 plus theta. Yes or no? Effective G would then be the resultant of this G, and this G sine theta would give me the effective G. Would give me the effective G. This G and this G sine theta with this angle being 90 plus theta would give me the effective G for the situation. G effective then is going to be given by root G square plus G square sine square theta plus twice G into G sine theta into cos 90 plus theta right? Cos 90 plus theta will be minus sine theta. Minus sine theta. So this will become, this becomes minus sine theta. So this will become minus sine square theta. So the G square plus G square sine square theta minus 2G square sine square theta would be G squared minus G square sine square theta. Yes or no? Right? Which is G square cos square theta so the G effective then becomes G cos theta the time period of this is going to be 2 pi root L by G cos theta L by G effective, which is G cos theta. So far so good, right? Now let me explain to you. So this was a simple pendulum. We also have what's called a physical pendulum. Let us look at what a physical pendulum is. But so far so good, right? A physical pendulum with small little variations here and there. This is how it goes. Okay. Suppose this is a laminar body. Plain laminar body, say of mass m. And this is where it's hinged. It's hinged at a certain point A, pinned at a certain point A. So this is like the point of suspension. This is the point of suspension. A is the point of suspension. Clear? The center of mass will be along a line passing through A. Somewhere here, the center of mass will lie. Center of mass will lie. And mg will act like this. The unit is suspended vertically. The unit is suspended vertically under the influence of gravity. Now, I swivel this in the anti-clockwise sense, say. So it will swivel about A. Once I swivel it about A and say the distance between the center of mass and A, let's say, is L. L is the distance between the center of mass and A. Now when I swivel it, the center of mass will move in a circle of radius L centered at A. Right? So after a while you would see, say, the center of mass somewhere here, length L. This is the center of mass somewhere here. Clear? And I have swiveled it anti-clockwise. I have swiveled it anti-clockwise. And say this angle is theta, the amount by which I have swiveled this. Clear? Now, do you see that this laminar body will experience, after you displace it anti-clockwise, it will experience a clockwise torque. Why? Because this mg produces a clockwise torque about A. This mg will produce a clockwise torque about A. And if this length is L, this length is going to be L sine theta. This length is going to be L sine theta, right? So the torque about A that it produces is going to be mg, whose line of action is this. And the perpendicular distance of the line of action of mg from A is this, yes or no? Which is the same as L sine theta. Perpendicular distance of the line of action of mg from A is L sine theta. So mg into L sine theta, right? Mg into L sine theta is a torque which is restoring in character. It wants to bring it back to this vertical state, right? Right? And it is clockwise in sense. Now the torque is also given by moment of inertia of this rigid body about an axis passing through A and perpendicular to the plane, right? This is the axis of rotation, right? This rigid body would execute, this would be in a state of pure rotation with an axis of rotation passing through A. Yes or no? So I about A, torque about A is given by I about A into d2 theta dt2 like before. D alpha dt is d2 theta dt2. That's the torque about A, right? Now, this torque is clockwise, so it should be written as minus mgl sine theta. If I've chosen anti-clockwise positive and clockwise negative, then it should be written as minus of this, right? No? Clear? Which means d2 theta dt2 would be minus mgl by I about A. Now, if theta is small, like before, sine theta is approximately theta. So this sine theta I can replace by theta. So this is like some minus omega squared into theta, right? Where omega squared is mgl by I about A, moment of inertia of this rigid body, planar rigid body about an axis passing through A and perpendicular to the plane of the lamina. Which means now the body will execute angular SHM. See, d2 theta dt2 is minus a positive constant into theta, so it's going to be a case of angular SHM. This is going to be a case of angular SHM, right? Whose angular frequency will be this much, right? Omega, the angular frequency of oscillation, is going to be root mgl divided by I about A. The time taken to complete a full oscillation is going to be 2 pi by omega. Yes or no? Right? And this arrangement is called a physical pendulum. It's called a physical pendulum. This is a physical pendulum. IA is the moment of inertia of this lamina about the point of suspension perpendicular to the plane of the lamina. Right? Now, from parallel axis theorem, do you realize that I about A is going to be I about VCM plus ML squared, I about CM plus ML squared? Parallel axis theorem. I about an axis passing through A is going to be I about an axis passing through CM plus ML squared. L is the distance between the point of suspension and the center of mass of this rigid body. Now, if K is the radius of gyration about an axis passing through the center of mass, K is the radius of gyration about the center of mass axis, then do you realize ICM can be written as mk squared? Then ICM can be written as mk squared. K is the radius of gyration about an axis passing through the center of mass and perpendicular to the plane of the lamina, right? So time period, follow this formula for this physical pendulum is going to be 2 pi root I about it, this axis, mk squared plus ml squared divided by gl. Right? Yes or no? Now, the center of mass is where it is, but the point of suspension can be varied. The point of suspension can be varied. Now notice that if I vary L, on which K is a constant, right? Because it's related to the center of mass. L is the distance of the point of suspension from the center of mass, which could be varied. So the time period of this physical pendulum could vary if I vary L, the point of suspension. Now, K squared plus L squared by L. This is the number that will determine the value of T. K squared plus L squared by L, because G is a constant. Right? This is actually K squared by L plus L. Yes or no? If this is minimum, T will be minimum. If this is minimum, T will be minimum, right? Now, one thing for sure, you can see that as L becomes smaller and smaller, K squared by L becomes larger and larger, and therefore time period tends to infinity, right? If L becomes larger and larger, then this will become smaller and smaller, but this will become larger and larger. So again, time period tends to infinity, which means you would expect something like this. Notice, time period versus L, one thing. As L comes closer and closer to 0, time period is very large, going up. And as L tends to infinity, time period again is going higher and higher, which means I would expect, you know, without doing too much of mathematics, I would expect time period versus L to be a cup-shaped structure like this, and I would expect at a certain value of L equal to L naught, I would expect T to be T min. I would expect this. I would expect T to become T min somewhere. Right? Now, so T would be T min when this is min. Right? T would be T minimum when this is minimum. Now, K squared by L plus L by 2. That's an arithmetic mean between these numbers. That's an arithmetic mean between these numbers, and it must always be greater than or equal to the geometric mean. Geometric mean is root K squared by L into L. That's a geometric mean between these numbers. Right? Which means K squared by L plus L must be greater than or equal to 2K. Arithmetic mean greater than or equal to geometric mean. That means the minimum value of this is 2K, right? The minimum value of this expression is 2K. That means minimum value of K squared by L plus L is 2K. Now, this will be 2K when arithmetic mean will be equal to the geometric mean. When AM equals GM, that's when it will be 2K, right? This will happen when arithmetic mean becomes equal to the geometric mean between these two numbers, K squared by L and L. K squared by L and L are two entities, right? Now, when AM becomes equal to GM, when would AM become equal to GM? When the quantities involved in their constitution are equal. This would happen when k squared by L becomes equal to L. This would happen when k is L, rather when L is k. That means this L naught must be equal to k. For T to be T min, for T to be T min, L naught must be equal to k, the radius of gyration about the center of mass axis. Got me? So this is the story of a physical pendulum. They would give you regular geometries, and it could be a square or a rectangle or a circular disc hinged about a point A, and you could find the moment of inertia about specific points by using parallel axis theorem and so on and so forth. Clear?